So here's a question for you. Some of you out there like to drink soda with lots and lots of sugar in it. You know, the very sweet kind that, when you drink, it tastes very sweet on your tongue. And some of you like to drink quite a lot of it. So here's a question for you. How much sugar is there actually in that stuff that you're drinking? So you can go and look on the label of the container to find that out. But instead, I'm going to ask you in a slightly different way. What's the sweetest drink you can possibly make? So this is what I want you to imagine. Suppose I take a jar which has in it, I don't know, let's say it has a pound of water in it. And then suppose I take another jar which has a pound of sugar. Do you think you can dissolve the pound of sugar into the pound of water? So what I mean by that is if you pour the sugar into the water and you stir, do you think that it'll look, all of the sugar will dissolve and none of it will come out at the bottom? Imagine that you were to do the same thing with salt. So imagine you can take a pound of water and a pound of salt. And you took the salt and you poured it into the water and you stirred. Do you think all the salt would dissolve? Let me tell you the answer. So it turns out that all of the salt would not dissolve. In fact, the solubility of salt is about 1/3 of a gram per gram, which essentially means if you took a pound of salt and tried to pour it into a pound of water, 1/3 of a pound would dissolve and the other 2/3 would come out at the bottom as white powder. If you don't believe me, you should go try it. Just take some salt, measure out the weight of the water, measure out the weight of the salt, pour it in, and you'll see that only about 1/3 of the mass of water in salt will actually dissolve. If you do it with sugar, on the other hand, totally different thing. The pound of sugar will dissolve perfectly. You can actually take the whole pound of sugar, pour it in water, and have it dissolve. But it's even worse than that. The solubility of sugar is actually 2 grams per gram, which means you can actually take 2 pounds of sugar and pour it into a pound of water and it will all dissolve perfectly and you can drink it. So actually, if you think about it, much of cooking, or many things that we eat or mainly drink involve dissolving one thing in another thing. So I, for example, like to drink coffee. So every morning I take coffee and I pour hot water over the coffee, and some of the molecules from the coffee get into the liquid and it's sort of dissolved. And then, I drink that and it makes me have more energy. Others like to drink tea. And many things, actually, if you think about it, involve dissolving one substance into another. And so the question that I want to ask now is, what is the physics of that? What sets how much of one thing can you dissolve in the other? Why is the solubility of sugar so much more than the solubility of salt? So that is the question for the moment. If you look at the shape of sugar before you put it in the water, it actually is a crystal. If you look at it under the microscope, you see that it's a solid and it's a crystal and it's making, there's sort of bonds and lattices between them. And what's physically happening is you pour the sugar crystal into the water and it then comes apart into a sea of sugar molecules that are dissolved in the liquid. So does that remind you of anything that we've discussed up until this point? We've taken a solid, namely that of sugar, we've put it into another substance, and then the molecules come out and fill the space like a gas. So the solubility of any compound, sugar or salt or anything else, is very, very much like, essentially almost exactly like the phase transition between a solid and a gas, which we've already, of course, discussed at length. And indeed, the physical principle that governs the dissolution of one substance in another is very much analogous to the physical principles that govern when a material is a liquid and when it is a gas. We sort of described it in 2 different ways. We said that the liquid-gas transition is described by this wonderful formula, U interaction is equal to C kBT, where the interaction energy is what we call the sticking. It's the fact that the molecules want to stick to each other on one hand, and the C kBT is the jiggling. It's the fact that the molecules like to jiggle around. If we apply the same idea to the sugar molecules, which are coming off of the crystal, the same thing applies. The sugar molecules have one interaction energy when they're within the crystal. They like being in the crystal. On the other hand, when they come off of the crystal and are dissolved, are sort of in the water by themselves, 2 things happen. The first is they're surrounded by water molecules, which they don't hate either. They don't like them as much as they like being in the crystal, but it's not a bad thing for them. But even more importantly, they can jiggle. They have entropy. They can move. And so it's this competition between jiggling on one hand, the fact that they would like to jiggle, and sticking on the other hand, the fact that they would like to stick to each other, that leads to the question of how much you can dissolve. So another way of saying the same thing, which we've also discussed, is to talk about the competition between energy and entropy. On one hand, when the sugar molecule is in the crystal, it's sticking to bunches of its neighbors, and it gains some energy from that relative to when you release it and put it in the water. And on the other hand, when you release it, it has entropy. It has the freedom to explore volume, and that actually creates a driving force to basically make it move around in the liquid. And so the question of dissolution of taking a solid sugar cube and dissolving it in a liquid is the same competition between energy and entropy that we've already discussed previously. And for that reason, we can literally apply the same equation of the week that we did for the phase changes of matter to dissolution. Namely, the solubility limit occurs when the interaction energy is equal to some constant times kBT. It's the same physics. The only thing that's changed here is the constant, whereas we told you that for simple phase transitions, that constant was 3/2 or whatever, some number depending a bit on the substance. It was 3/2. In this case, it really depends on the situation a little bit more. And so I'm going to show you a slightly more complicated formula for this constant, which exposes the physics in more detail. And that formula is that the constant is actually the logarithm of the volume of the gas. It's the volume that each molecule of the sugar takes up when it's released into the liquid, divided by the volume that each molecule of the sugar takes up when it's in the solid, divided by a number that we call Z, which is the sort of number of neighbors that the sugar molecule has when it's in the crystal. This is a bit of a complicated formula, and I'm not asking you to understand it in really any detail. I'm putting it here to sort of show you the different factors that are involved. But the main point that I really want to emphasize here is that the physics of dissolution is very, very similar, closely analogous to the physics of a phase transition. But for the case of solubility, there's another way we can rearrange this formula that's actually particularly useful, which is that we can solve for the concentration of the salt in the solute. That is, if you're drinking sugar water, if we go back to the very beginning, what you should really be worried about when you're drinking the Coca-Cola is what is the concentration of sugar that's in this Coca-Cola after all anyway? I mean, if it's low calorie, then we hope that it's not very much, for example. And so for that, we can take this formula and solve for the concentration of solute, and it gives this nifty formula that the concentration of solute is equal to the concentration in the solid times e to the minus interaction energy times the number of contacts over kBT. So this is this beautiful formula. It was a formula that was first invented by Ludwig Boltzmann, a great physicist in the 19th century, and it tells you what the concentration of solute is like. And what you see from this is it depends on the concentration in the sugar, which is basically just the density. It's set by the density of sugar, and it also depends on the temperature and the interaction energy. So one aspect of this formula is particularly important for candy making, which we are going to discuss rather soon, which is that you'll notice from this formula that when you increase the temperature, then the concentration in the solute actually goes up quite substantially. And so as an example, so here is data actually which shows the solubility of sugar as a function of temperature. So you'll remember that at room temperature, you were all probably appalled, as I was, to learn that you can dissolve 2 pounds of sugar in 1 pound of water. So it turns out if you go up to the boiling point of water, then you can dissolve 4 pounds of sugar in 1 pound of water. The solubility actually goes up by a factor of 2. And it continues to go up as you increase the temperature. That is, the concentration of sugar that you can dissolve goes up and up until some critical temperature when you basically just have sugar. And this simple fact that the solubility curve looks like this and has the temperature dependence that we're describing is very important for candy making. It is, without this, you would not have candy as you know it. And this is something that we will discuss a little later on. So there's one more point that I would like to make in order to close this section, which is that, so remember I told you that the solubility of sugar at room temperature is 2 grams per gram, whereas the solubility of salt is 1/3 of a gram per gram. So you might wonder, why are these numbers so different? This is also a fact. It's a simple scientific fact that really has great impact on cooking, that you can't make a water as salty as you can sweet. Has great impact. And it turns out that the reason in this case is peculiarly very simple. So it turns out that, remember, the weight of 1 mole of sugar is about 342 grams, whereas the weight of 1 mole of salt is about 58 grams. So there's about a 6-fold difference between the molecular weight of sugar and salt. So if you remember the solubilities, the 2 grams per gram and 1/3 of a gram per gram, they also differ by a factor of 6. So that means that actually what's happening when you dissolve sugar and salt in water at room temperature is that the number of molecules in a given volume is actually about the same, that both substances, what you're setting equal is the number of molecules, and that is telling you that the difference in solubilities is really mainly an entropic effect. It's not an energetic effect, it's an entropic effect. Now, I caution to tell you that this is a fact that's really only true at room temperature. If you go up to 100 degrees Celsius, where the solubility of sugar has doubled, the solubility of salt has not doubled by that point, and so there are energetic effects at play too. But it's just sort of interesting that the main qualitative difference between what we showed you at the very beginning of this section has to do with the differing molecular weights of the two materials.